Yo guys, so tonight we are gonna go through literally everything there is to know about geometry, from the history to how it works. We are gonna go through every concept, every calculation, just everything. And then at the end, we are gonna look at some theories and predict how geometry can be used in the future. This took quite a long time to make, so whether you are falling asleep to this or just relaxing, watching Bub over here float through space, enjoy. And let's start with the history of geometry. So let's go back to the very beginning. The story actually starts before Egypt, way before. We're talking about prehistoric humans who, somewhere around 30 or 40,000 years ago, were already noticing geometric patterns and putting them on cave walls, spirals, zigzags, grids of dots. Nobody knows exactly what those meant, but people were clearly drawn to patterns and shapes, even before anyone had words for them. The brain is genuinely good at this. You don't teach a kid what a circle is, they recognize it. You don't explain to someone that two lines going in the same direction will never meet. They kind of already get it intuitively. Geometry isn't some invented thing humans created out of nowhere. It's more like a language we slowly discovered for something we already half knew. But then you get these early civilizations, Mesopotamia and Egypt, roughly 3000 BCE, and things get serious. These weren't people drawing spirals for fun. These were people who had cities, irrigation systems, granaries, tax records, and enormous building projects. And all of that required actual math. The Babylonians, who lived in what's now Iraq, were writing on clay tablets. Clay is durable, so we actually have some of their work, and what they left behind is genuinely shocking for something so old. They knew about the relationship between the sides of a right triangle more than 1,000 years before a guy named Pythagoras was even born. There's a tablet called Plimpton 322, dated to around 1800 BCE, and it has lists of what we'd now call Pythagorean triples. Sets of three numbers, where the square of the biggest one equals the squares of the other two added together, like 3, 4, 5, or 5, 12, 13. They had hundreds of these, and they clearly understood what they were doing. They also calculated pi, the ratio of a circle's circumference to its diameter, and got it to be about 3.125. That's only off from the real value by about 0.5%. Not bad for people using clay and a reed pen. The Egyptians were doing similar things, but through a slightly different lens. The word geometry literally comes from Greek, geo meaning earth and metron meaning measurement. But the Egyptians had their own word for the people who did this work. They called them rope stretchers, because that's what land surveyors actually did. You stretch a rope between 2 points, and that gives you a straight line. You stretch 3 ropes in a triangle, and you can define a piece of land. That's simple in practice. And underneath, it is an entire abstract system that would take another 2,000 years to fully articulate. The Egyptians figured out the area of a circle by a method that assumed pi was about 3.16. Not perfect, but still remarkable. They also figured out the volume of a frustum, which is what you get when you cut the top off a pyramid. That formula is genuinely difficult. Modern mathematicians looking at it have said that to derive it without calculus or algebra takes some serious work. The Egyptians just had it, written in a papyrus called the Moscow Papyrus, roughly 1,000 850 BCE. And speaking of pyramids, the Great Pyramid of Giza, built around 2560 BCE, is a geometric achievement that still makes people's jaws drop when they look at it closely. The base is a nearly perfect square. We're talking 4 sides, each about 230 meters long, with a difference between the longest and shortest side of less than 20 centimeters. The 4 corners are almost perfect right angles within a fraction of a degree. The whole thing aligns with the cardinal directions to within a tiny fraction of a degree. This was done without GPS, without laser levels, without any of the tools we'd use today. Just ropes, plumb bobs, sighting instruments, and a tremendous amount of knowledge about geometry that was passed from teacher to student over generations. How did they do the right angles? One theory, and there's real evidence for this, is that they used a rope with knots tied at specific intervals to make a 3, 4, 5 triangle. 3 units on one side, 4 on another, 5 on the hypotenuse, and that gives you a perfect right angle. Every time it works because of the very relationship the Babylonians had on those clay tablets. The Egyptians were literally using Pythagorean triples to build pyramids about 1500 years before Pythagoras. The thing about all this early geometry though, it worked, but nobody was asking why it worked. You just had a collection of rules, procedures, do this to get that. If the shape is roughly a circle, multiply the diameter by itself, take 8/9 of that diameter first, and you get the area. Nobody knew why that worked, nobody had proven it. It was discovered through trial and error, refined over centuries, passed down as technique. That's about to change in a very big way. Around 600 BCE, something weird started happening in Greece. A bunch of philosophers and thinkers began asking a different question. Not, does this rule work? But, why does this rule work? How do we know it's always true? This is a genuinely strange thing to care about. If you're a farmer or a builder or a tax collector, you don't need to know why the rope triangle gives you a right angle. You just need to know that it does. But the Greeks, some of them anyway, started getting obsessed with certainty, with proof, with the idea that you could start from a few things you accept as obviously true and then derive everything else through pure logic. The first name in this story is Thales of Miletus. He lived roughly from 624 to 547 BCE, and he had traveled to Egypt, studied their methods, and come back to Greece with a head full of geometric techniques. But he didn't just use them, he started proving them. He's credited with several theorems, including that a circle is bisected by its diameter, which sounds obvious, but you have to prove it, and for insisting that geometric statements needed logical justification, not just empirical verification. Then comes Pythagoras. He was born around 580 BCE, traveled even more widely than Thales, and founded a kind of mathematical cult in southern Italy, the Pythagorean Brotherhood, where geometry was considered almost a spiritual pursuit. The theorem that bears his name, that in a right triangle, the square on the hypotenuse equals the sum of the squares on the other 2 sides, was almost certainly known before him in some form. But he, or his followers, gave the first recorded formal proof of it. A proof is a big deal. It's the difference between this works in all the cases we've tried and this must be true always and everywhere, and the logical chain shows why. Once you have a proof, the thing is true, not probably true, not true so far, true. The Pythagoreans also made a discovery that genuinely terrified them, and according to some accounts, they tried to suppress it. When they applied the Pythagorean theorem to a square with sides of length 1, they found that the diagonal had a length equal to the square root of 2, and the square root of 2 cannot be written as a fraction. It's irrational. It goes on forever without repeating. The Pythagoreans believed deeply that all of mathematics should be expressible through whole numbers and their ratios. The existence of irrational numbers was a philosophical catastrophe for them. There's a story, possibly apocryphal, that a man named Hippasus proved the irrationality of the square root of 2 and was drowned for it. The Greeks kept building. Democritus, who's better known for his atomic theory, figured out the volume of a cone and pyramid using methods that were getting close to calculus. Eudoxus developed a method of exhaustion where you figure out a curved area by filling it with polygons of increasing number and smaller size, and the result gets closer and closer to the true area. Sound familiar? That's basically what calculus does. And then Euclid. Around 300 BCE in Alexandria, Egypt, which was then a Greek intellectual center, a man named Euclid wrote a book called Elements, and this book changed everything. For more than 2,000 years, it was the standard textbook for mathematics education in the Western world. Abraham Lincoln used to study it as a young man to train himself to think rigorously. It was that important. What Euclid did in Elements was take all the geometric knowledge that had accumulated over centuries, from the Babylonians to the Egyptians to the Greeks, and organize it into a single logical system. He started with 5 postulates, things so obvious they barely needed stating. Things like, you can draw a straight line between any 2 points, or all right angles are equal to each other. Just 5 simple starting points. And then, from those 5 starting points alone, using only logic, he derived 465 theorems across 13 books. Everything from the properties of triangles and circles to the theory of proportions to the existence of exactly 5 regular solids, the tetrahedron, cube, octahedron, dodecahedron, and icosahedron, now called the Platonic solids. Each theorem proven from previous theorems, all the way back to the 5 postulates at the start. It's one of the most impressive intellectual achievements in human history, not because all the individual results were new. Many had been known before, but because of the structure, the idea that a single unified logical system could contain all of this. That geometry wasn't just a bag of tricks, but a coherent, deductive edifice. Let's slow down and look at some of the actual concepts Euclid worked through, because this is where we start to see what geometry actually is. At the bottom of all geometry are a few basic things you can't really define in simpler terms. A point is a location, no size, no length, just position. A line is a collection of points that extends in both directions infinitely with no width. A line segment is a piece of a line with 2 endpoints. A ray is like half a line, starts at a point and goes in one direction forever. From these basics, you build everything else. 2 lines in the same flat plane can do one of 2 things. They can intersect at exactly 1 point, or they can be parallel, meaning they go in the same direction and never meet. That's it. Those are the only options in flat geometry. When 2 lines meet, they form angles, and angles are measured in degrees, with a full circle being 360 degrees. A right angle is 90 degrees. An acute angle is less than 90. An obtuse angle is between 90 and 180. A straight angle is exactly 180, which is just a straight line, looked at from a different angle, pun intended. Now take 3 line segments and connect them end to end, and you get a triangle. Triangles are kind of the atoms of geometry. Everything more complicated can be broken into triangles. And the most basic fact about any triangle in flat space is that its 3 interior angles always add up to exactly 180 degrees. Always. You could draw 10 million different triangles of wildly different shapes and sizes, measure all 3 angles in each one, and you'd always get 180. That's a provable fact, not a lucky coincidence. Different triangles have different properties. An equilateral triangle has all 3 sides the same length and all 3 angles equal to 60 degrees. An isosceles triangle has 2 equal sides and 2 equal base angles. A scalene triangle has all 3 sides different lengths. And then there's the right triangle, where one angle is exactly 90 degrees, which is the one Pythagoras was obsessed with. The Pythagorean theorem, in plain language, goes like this. You have a right triangle. The side opposite the right angle is called the hypotenuse, and it's always the longest side. If you draw a square on each of the 3 sides, the area of the square on the hypotenuse equals the area of the squares on the other 2 sides added together. That's it. That's the whole theorem. Why does this matter so much? Because it lets you calculate distances. Say you're at the bottom left corner of a rectangular field, and you want to know how far it is to the top right corner. You know the field is 300 meters wide and 400 meters long. You can't measure that diagonal directly. Maybe there's a pond in the way. But you square 390,000, square 160,000, add them 250,000, and take the square root, 500 meters. You got the answer from the 2 sides you could measure. That's genuinely useful. Beyond triangles, you get quadrilaterals, 4-sided shapes, squares, rectangles, parallelograms, trapezoids, then pentagons, 5 sides, hexagons, 6 sides, and on and on. The general name is polygon. And as you add more sides, something happens. The polygon starts looking more and more like a circle. An infinite-sided polygon, if that were a thing, would just be a circle. A circle is every point that's a fixed distance from a center. That fixed distance is called the radius. The diameter is twice the radius. It goes all the way across the circle through the center. And the circumference is the distance around the edge. The ratio of the circumference to the diameter is always the same number for every circle in existence, regardless of size. That number is pi, about 3.14159, and then it keeps going forever, without repeating. Pi is irrational, like the square root of 2. It can't be written as a fraction. People have now computed pi to over 100 trillion decimal places, and it still hasn't started repeating. To find the area of a circle, you use pi times the radius squared. Why? Because of that same infinity argument Eudoxus was playing with. You can think of a circle as being made up of infinitely many tiny triangles with their tips at the center, And when you add up all their areas, you get pi times r squared. Now, all of this, points, lines, angles, triangles, circles, polygons, this is what people usually mean by geometry. The flat, two-dimensional stuff you learned in school. But Euclid wasn't only dealing with flat shapes. The later books of Elements go into three-dimensional solid geometry. Three-dimensional shapes. Cubes have 6 square faces, 12 edges, 8 vertices. A tetrahedron, triangular pyramid, has 4 triangular faces, 6 edges, 4 vertices. A sphere is the three-dimensional version of a circle. Every point on its surface is the same distance from the center. The volume of a sphere is 4/3 times pi times the radius cubed. The surface area is 4 times pi times the radius squared. Archimedes, who came just a bit after Euclid and was arguably an even more extraordinary mathematician, proved these formulas and was so proud of the sphere-cylinder relationship that he reportedly asked for a sphere inscribed in a cylinder to be carved on his tombstone. Archimedes, 287 to 212 BCE, also came up with a brilliantly clever way to calculate pi more precisely. He took a circle and drew regular polygons inside and outside of it, hexagons first, then 12-sided, then 24-sided, then 48-sided. The circle has a circumference between the perimeters of the inner and outer polygons, and as you use more sides, those bounds get closer and closer together. He got to 96-sided polygons and concluded that pi is between 223 sevenths and 22 sevenths. That's between 3.1408 and 3.1429. The actual value is 3.14159. He was incredibly close. Archimedes was genuinely a once-in-a-generation mind. He proved formulas for the area of a parabolic segment, figured out volumes of various curved solids, developed the concept of centers of gravity, and basically got right up to the edge of calculus, which wouldn't be formally invented for another 1900 years. His work was so far ahead of his time that it wasn't fully appreciated until translations of it spread through Europe in the 17th century. He also reportedly proved something beautiful. The area inside a circle of radius r equals the area of a right triangle with legs r and 2 pi r. It's elegant in a way that's hard to describe if you haven't seen it. The simplest shape and the most fundamental curved shape related through that triangle. It's the kind of result that makes you feel like mathematics is showing you something real about the structure of the world. After Euclid and Archimedes, the Greek tradition kept going for a few more centuries before gradually declining. A few names worth knowing. Apollonius of Perga, around 200 BC, wrote a massive treatise on conic sections. A conic section is what you get when you slice a cone with a flat plane at different angles. Slice it parallel to the base and you get a circle. Tilt the slice a bit and you get an ellipse. Tilt it more until it's parallel to one side of the cone and you get a parabola. Tilt it even more steeply and you get a hyperbola. These 4 curves, circle, ellipse, parabola, hyperbola, turned out to be unbelievably important. Planets orbit in ellipses. Projectiles follow parabolas. Radio telescope dishes are parabolic. And hyperbolas show up in physics and engineering constantly. Apollonius worked all of this out in extraordinary detail around 2,000 years before anyone knew why it mattered for the real world. Heron of Alexandria, roughly 1st century CE, came up with a formula for the area of a triangle given only the lengths of its 3 sides. No need to know the angles or height. His formula is area equals the square root of S times S minus A times S minus B times S minus C, where A, B, C are the 3 sides and S is half the sum of all 3 sides, called the semi-perimeter. Go try it on any triangle. It works every time. It's one of those results that feels almost magical until you go through the proof. Ptolemy, roughly 100 CE, wrote the Almagest, which was primarily an astronomy text, but was full of geometry, specifically spherical geometry for calculating positions of stars and planets. He developed a lot of what we now call trigonometry, the study of the relationships between angles and side lengths in triangles. His table of chords was essentially a table of sines in disguise. Pappus of Alexandria, around 300 CE, was the last major Greek geometer. His major work collected and extended a huge range of earlier results and introduced some new ones, including the beginnings of what would later become projective geometry. And then the political situation in the Mediterranean deteriorated. The Roman Empire had other priorities, and the Greek mathematical tradition essentially stopped. There wouldn't be anything comparable in Europe for over 1,000 years. Something not enough people know. A huge amount of what we consider Greek mathematics would be completely lost if it weren't for Islamic scholars of the 8th through 14th centuries. When the Islamic Empire expanded rapidly in the 7th century CE, scholars in Baghdad, Damascus, Cairo, and elsewhere began systematically translating Greek texts into Arabic. The Library of the House of Wisdom in Baghdad, founded around 800 CE under the Caliph Harun al-Rashid and expanded by his successor al-Ma'mun, became one of the greatest intellectual centers the world had ever seen. Scholars there translated Euclid's Elements, Archimedes, Apollonius, Ptolemy, and many others. If those translations hadn't happened, we might have lost those texts entirely, since the original Greek manuscripts often didn't survive. But these scholars didn't just translate. They extended and improved. Al-Khwarizmi, whose name gives us the word algorithm, and whose title Al-Jabr gives us algebra, lived around 780 to 850 CE and developed systematic methods for solving equations. This might seem like it's about algebra rather than geometry, but at the time, these things were deeply intertwined. Geometric methods were used to justify algebraic operations. Thabit ibn Qurra, 836 to 901 CE, was extraordinary. He translated huge amounts of Greek mathematics, corrected errors in previous translations, and proved a general version of the Pythagorean theorem. He was also working on geometric problems that wouldn't be solved in Europe for centuries. Omar Khayyam, who you might know as a poet, was also a serious mathematician. In the late 11th century CE, he worked extensively on Euclid's 5th postulate, the parallel postulate. He couldn't prove it, but his attempts led him to geometries that were non-Euclidean without him quite realizing it. Ibn al-Haytham, 965 to 1040 CE, known in the West as Al-Hazen, wrote a massive work on optics that was profoundly geometric. He proved how lenses and mirrors work using geometric principles of reflection and refraction. His work influenced Kepler and Descartes 700 years later. Al-Tusi, in the 13th century, analyzed Euclid's parallel postulate more deeply than anyone before him, and produced what's called the Al-Tusi couple, a geometric mechanism describing how a circle rolling inside another circle traces a straight line. That result would later influence Copernicus's model of planetary motion. The Islamic geometers were also extraordinary in applied geometry. Islamic architecture is full of geometric complexity, intricate tile patterns called girih tiles that cover entire mosque walls with repeated geometric patterns of stunning complexity. In 2007, a team of physicists and mathematicians analyzed some of these patterns from 15th century CE Islamic buildings and found quasi-crystalline geometry, patterns that are non-repeating but still have a kind of order, the same kind of structure that was discovered in Western mathematics in 1984. Medieval Islamic craftsmen were using these patterns 500 years before mathematicians could explain them. Europe was slowly waking up to mathematics in the late medieval period, partly by encountering Arabic texts through Spain and Sicily, which had been under Islamic rule and retained strong Arabic scholarly traditions. Fibonacci, the 13th century Italian mathematician, famous for the sequence that bears his name, introduced the Hindu-Arabic numeral system to Europe, the 0 through 9 system we still use. His book also contained a lot of geometry, but the transformative moment came in the 16th and 17th centuries, and one thing that made it possible was the printing press. Euclid's Elements was one of the first mathematics books printed in Europe in 1482. It went through hundreds of editions over the following centuries. Then, in 1637, René Descartes, a French philosopher and mathematician, published an appendix to one of his philosophical works called La Géométrie, and this appendix, almost as a side note to the main text, completely transformed mathematics. Descartes connected geometry and algebra in a way nobody had done before. He said, put a grid on the plane, call horizontal position x and vertical position y. Now any point in the plane corresponds to a pair of numbers. Any curve in the plane corresponds to an equation relating x and y, and vice versa. Any equation in x and y traces out a curve. This is the Cartesian coordinate system you used in every math class, and it sounds simple now, but at the time it was a revolution. Suddenly, you could take a geometric problem and turn it into an algebra problem, or take an algebra problem and see it as a geometric picture. These two massive areas of mathematics were revealed to be different languages for the same thing. The parabola that Apollonius had spent a whole book studying, it's just y equals x squared. The circle of radius 5 centered at the origin, x squared plus y squared equals 25. The relationship between geometry and equations became so tight that you could switch between them whenever it was convenient. Descartes shared credit for this insight with Pierre de Fermat, who developed essentially the same idea around the same time independently. This sort of simultaneous discovery happens a lot in math history. When an idea is ready to emerge, it tends to emerge in multiple places at once. This analytic geometry through algebra and coordinates, made everything suddenly more computable, and it set the stage for the next massive leap, Isaac Newton and Gottfried Leibniz independently invented calculus in the 1670s and 1680s. Newton was motivated largely by physics. He needed mathematical tools to describe motion and gravity. Leibniz was more interested in the abstract mathematical structure. They ended up in a bitter priority dispute that their respective fans continued long after both men were dead. But for geometry, calculus was a game changer. Because now you could study curved shapes, surfaces, volumes, lines. In a completely general way, you could calculate the length of any curve. You could calculate the area under any curve. You could calculate the volume of any solid, and you could do this for things that weren't simple circles and cones, any shape describable by an equation. More importantly, calculus introduced the idea of studying things locally. In flat Euclidean geometry, a surface is either flat or it's not. But calculus lets you zoom in on any surface until it looks approximately flat, do your calculations there, and then integrate over the whole thing. This was the key that would eventually unlock the door to understanding curved spaces. And the first major example of that was the geometry of the surface of a sphere, spherical geometry. Think about what happens to Euclid's rules when you're working on the surface of a ball. The straight line between 2 points on a sphere, the shortest path, is an arc of a great circle. The equator is a great circle. The lines of longitude are great circles. Lines of latitude that aren't the equator are not great circles, they're shorter paths. On a sphere, parallel lines don't exist in the Euclidean sense, because any two great circles must intersect at two antipodal points. Every pair of lines meets, and the angles of a triangle on a sphere don't add up to 180 degrees, they add up to more. Draw a triangle on a globe. Start at the North Pole, go down to the equator, travel 90 degrees along the equator, then go back up to the North Pole. Each angle at the base of that triangle is 90 degrees. The angle at the top depends on your path. If you went a quarter of the way around the equator, that top angle is also 90 degrees. So your triangle has three 90-degree angles. That's 270 degrees total, not 180. Sailors and navigators had been dealing with spherical geometry for centuries, calculating distances across oceans, plotting star positions, figuring out how to get from one point on a globe to another via the shortest route. But it had always been treated as a special case, an application. The idea that it might be a completely different geometry with its own rules took a long time to crystallize. Let's go back to Euclid for a moment and talk about that fifth postulate. Because this one thing, this one seemingly minor technical statement, caused more mathematical trouble over 2,000 years than almost anything else in history. Euclid's first four postulates are all simple and obvious. You can draw a line between any 2 points. You can extend a line as far as you want. Given a point and a distance, you can draw a circle. All right angles are equal. The fifth postulate is different. It says roughly, if a line crosses two other lines and creates interior angles on one side that add up to less than 180 degrees, then those two lines will eventually meet on that side. In modern language, the equivalent statement is this: through any point not on a given line, there is exactly one line parallel to the given line. It sounds reasonable, but even Euclid seemed uncomfortable with it. He went out of his way to avoid using it. His first 28 theorems in Elements don't require it at all. And it was longer and more complicated than the other 4 postulates, more like something you'd prove rather than just assume. For 2,000 years, mathematicians tried to prove that the 5th postulate was a consequence of the first 4. If they could do that, they wouldn't need to assume it. It would just be a theorem. Hundreds of people tried. All of them failed. Often, they thought they had succeeded and someone else would find the flaw. In the early 19th century, 3 men independently reached a stunning conclusion. The 5th postulate cannot be proved from the other 4. And the reason it can be proved is that you can have perfectly consistent geometries where it's false. Carl Friedrich Gauss worked this out first, but didn't publish. He was worried about the controversy it would cause. In 1829, the Russian mathematician Nikolai Lobachevsky published a geometry where the parallel postulate is replaced by a different rule, through any point not on a line. There are infinitely many lines that don't intersect the given line. In 1832, the Hungarian mathematician János Bolyai published the same thing independently. This is hyperbolic geometry, and it's real, it's self-consistent. It has no contradictions, it just has different rules. In hyperbolic geometry, the angles of a triangle add up to less than 180 degrees. Not a little less, potentially way less. A triangle with 3 ideal vertices on the boundary of hyperbolic space has angles that all go to 0. It's a 0, 0, 0 triangle. The more spread out your triangle is in hyperbolic space, the smaller the angle sum. The best way to visualize hyperbolic geometry is to think of a saddle shape, like the surface you'd sit on if you were riding a horse. It curves away from itself in all directions. If you put a tiny flat piece on a saddle, the edges all bend upward. That's negative curvature, and locally the geometry on a saddle-shaped surface behaves like hyperbolic geometry. Flat Euclidean geometry has 0 curvature. Spherical geometry has positive curvature. Hyperbolic geometry has negative curvature. That's the 3 types for 2-dimensional surfaces. When Bolyai showed his work to his father, who had also spent decades trying to prove the parallel postulate, and asked Gauss for an opinion, Gauss famously wrote back saying that he'd worked out similar ideas himself but never published. Bolyai, furious that Gauss might claim credit, reportedly declared that Gauss was just trying to steal his discovery. The whole situation was a mess. But the mathematics was unambiguously real and new and important. Then, in 1854, Bernhard Riemann gave a lecture that extended this whole idea even further. Riemann was a young mathematician in Germany, and this lecture, his habilitation lecture, given to earn a professorship, was one of the most consequential mathematical talks in history. Riemann said, "Let's think about geometry in a totally general way. Instead of assuming space is flat or has some specific curvature, let's create a framework where the curvature can vary from point to point, where the geometry at any location depends on the local properties of the space." He introduced what are now called Riemannian manifolds, spaces that can curve and bend in arbitrary ways, where you can still calculate distances and angles, but those calculations depend on the local geometry. Riemann died young at 39 of tuberculosis. He didn't live to see how his framework would be used. But in 1915, Albert Einstein published the general theory of relativity, and it turned out that Einstein needed exactly Riemannian geometry to describe gravity. In general relativity, space isn't a flat backdrop. It's a curved Riemannian manifold whose curvature is caused by mass and energy. What we call gravity is just the curvature of space-time. Planets orbit the sun not because there's a force pulling them in a circle, but because the mass of the sun curves space-time around it, and the planets are following the straightest possible paths, called geodesics, through that curved space-time. Riemann's lecture was from 1854. Einstein's theory was from 1915. The gap was 61 years. Riemann built the mathematical tool without knowing what it would be used for, and then 60 years later, it turned out to describe the fundamental structure of the universe. That happens a lot in mathematics. While Lobachevsky and Riemann were shaking up the foundations of geometry, a parallel strand of geometry was developing that had very different origins. This one started with painters. In the 15th century, Italian Renaissance artists became obsessed with perspective. How do you paint a scene so it looks three-dimensional? So the parallel lines of a road seem to converge at a vanishing point on the horizon. Filippo Brunelleschi, who built the dome of the Florence Cathedral, apparently ran experiments demonstrating linear perspective. Leon Battista Alberti wrote about it. Albrecht Dürer in Germany designed mechanical devices for artists to create perspective drawings. The mathematical problem in perspective is strange. When you look down a long straight road, the two edges of the road appear to converge at a point on the horizon. But of course, in reality, the edges of the road are parallel. They never meet. In the geometry of what your eyes see, the geometry of perspective projection, parallel lines can meet. Their meeting point is the vanishing point. Projective geometry is the geometry of these perspective projections. In projective geometry, any two distinct lines in the plane must meet, either at a regular point or at a point at infinity, the vanishing point. There are no parallel lines. Every pair of lines meets somewhere. The projective plane is bigger than the ordinary plane. It includes the regular plane plus a line at infinity, where all parallel lines meet. This sounds weird, but it gives you a more symmetric theory. In projective geometry, points and lines are completely symmetric with each other. Any theorem about points and lines has a dual theorem where the words point and line are swapped. Girard Desargues, 1691 to 1661 CE, developed projective geometry in the 17th century, though it was largely ignored for over a century until rediscovered. Blaise Pascal, as a 16-year-old, proved a beautiful theorem about 6 points on a conic, now called Pascal's theorem. These were the foundations. Projective geometry became a big deal in the 19th century when mathematicians realized it was in some sense more natural than Euclidean geometry. Fewer special cases, more symmetry. Felix Klein unified all the different kinds of geometry: Euclidean, hyperbolic, elliptic, projective, through what he called the Erlangen program in 1872. His big idea was that each type of geometry could be characterized by the group of transformations that preserve it. Euclidean geometry is preserved by rotations, reflections, and translations. Projective geometry is preserved by projections. You could classify and compare geometries by looking at these groups of symmetries. This was a massive organizing insight. Suddenly, all these different geometries weren't separate subjects. They were related parts of a single, larger picture. Now we get to what is probably the weirdest and most mind-bending branch of geometry. It's called topology, and the best way to understand it is by contrast. Normal geometry, Euclidean geometry, spherical geometry, all the things we've talked about, cares about distances and angles. The exact shape of things matters. A square and a circle are completely different objects in Euclidean geometry. Topology doesn't care about distances or exact shapes at all. In topology, the only thing that matters is the connectivity of a space. What's connected to what you can deform into what, without tearing or gluing. A square and a circle are the same thing in topology. You can squish a square into a circle continuously without cutting or gluing, so they're topologically identical. But a circle and a figure 8 are different. To turn a circle into a figure 8, you have to pinch it at a point that changes the topology. There's a famous joke: topologists can't tell the difference between a donut and a coffee mug, because both of them have exactly one hole, the handle of the mug, the hole through the donut, and you can continuously deform one into the other. But you can't continuously deform either of them into a sphere or a ball. Those have no holes. The number of holes, technically the genus, is a topological invariant, something that doesn't change under continuous deformations. A sphere has genus 0, a donut torus has genus 1, a surface with 2 holes has genus 2, and so on. Topology was sort of invented by Leonhard Euler in the 18th century through a problem called the 7 Bridges of Königsberg. The city of Königsberg, now Kaliningrad in Russia, was built on 2 islands connected to the mainland by 7 bridges. The question: is there a path that crosses every bridge exactly once? Euler proved in 1736 that no such path exists, and his proof didn't care about the distances or exact positions of the bridges, only about which areas were connected to which. That's topological thinking. Euler also discovered a beautiful relationship for polyhedra: the number of vertices minus the number of edges plus the number of faces always equals 2. V minus E plus F equals 2. For a cube, 8 vertices minus 12 edges plus 6 faces equals 2. For a tetrahedron, 4 minus 6 plus 4 equals 2. This Euler characteristic of 2 is a topological property of the sphere. Any surface topologically equivalent to a sphere has Euler characteristic 2. A torus has Euler characteristic 0. Topology really took off as a formal subject in the late 19th and early 20th centuries. Henri Poincare, who comes up over and over in math history, was a major figure here. He essentially created algebraic topology, the idea of using algebraic structures, groups, rings to classify topological spaces. One of the most famous unsolved problems of the 20th century was the Poincare conjecture, which Poincare himself proposed in 1904. It says, any compact, simply connected three-dimensional manifold without boundary is topologically equivalent to a three-sphere. In plain language, if you have a three-dimensional closed space where every loop can be shrunk to a point, then it must be a three-sphere. Proving this turned out to be extraordinarily hard. The analogous result in higher dimensions was proved in 1961 by Stephen Smale for dimensions 5 and above, and in 1982 by Michael Friedman for dimension 4. But dimension 3 was the hardest. It wasn't proved until 2002 to 2003 when Grigory Perelman, a Russian mathematician working alone in St. Petersburg, posted a series of papers to Archive that proved it. As part of a more general result called Thurston's geometrization conjecture, Perelman was awarded the Fields Medal, the mathematical equivalent of a Nobel Prize, and the Millennium Prize, $1 million. He declined both. Topology shows up in unexpected places. The theory of knots, literally studying knots tied in a loop of string, and when two different looking knots are the same knot, is a branch of topology with connections to physics, chemistry, the way DNA coils and unknots, and quantum computing. Whether a linked pair of loops can be unlinked without cutting is a topological question. The topology of the universe itself, whether it's infinite and flat, or finite and closed like a sphere, or something more exotic, is an open question in cosmology. Let's go one level deeper into the geometry that connects to physics most directly. Differential geometry is the study of smooth, curved spaces using calculus. It's the language of general relativity and increasingly the language of modern physics in general. The key idea is this. Imagine you're an ant living on the surface of a very large sphere. From your perspective, the surface looks flat, like Euclidean geometry. If you walk a short distance in any direction, everything looks like a flat plane. But over longer distances, you'd notice things are off. Parallel lines you draw in different directions come back and meet. Triangles have angles summing to more than 180 degrees. And if you travel far enough in a straight line, you eventually come back to where you started. Differential geometry lets you make this precise. You describe a curved surface or higher dimensional manifold by saying that locally it looks like Euclidean space, but globally it can have curvature. The curvature is described by a mathematical object called the curvature tensor, and at each point in the space, the curvature tensor tells you how much and in what way the space is bending. Gauss showed that the curvature of a surface is an intrinsic property. It doesn't matter whether you embed the surface in a higher dimensional space. A two-dimensional creature living on the surface of a sphere could, in principle, detect the curvature by doing measurements within the surface itself, without needing to see the sphere from outside. Riemann generalized this to arbitrary dimensions. His Riemann curvature tensor describes the curvature of any manifold in any number of dimensions, purely from intrinsic measurements. When Einstein formulated general relativity, he used the Riemann curvature tensor to express how mass and energy curve spacetime. The Einstein field equations are essentially equations relating the curvature tensor, which describes geometry, to the stress-energy tensor, which describes the distribution of matter and energy. Geometry tells matter how to move. Matter tells geometry how to curve. One of the predictions of this theory was gravitational lensing. Massive objects like galaxies should bend light passing nearby, like a lens. This was confirmed in 1919 when observations during a solar eclipse showed stars that should have been hidden behind the sun were visible, their light bent around it. It was one of the most dramatic experimental confirmations of a scientific theory in history. Differential geometry is also the language of string theory, a proposed but not yet confirmed theory of quantum gravity. In string theory, the extra dimensions of space are not flat. They're curled up into tiny Calabi-Yau manifolds, which are six-dimensional geometrical structures with very specific curvature properties. The shape of these tiny hidden dimensions determines the properties of elementary particles in our universe. Different shapes give different particle physics. The details of these manifolds, which are studied using both differential geometry and algebraic geometry, are an active area of research. In 1975, a French-American mathematician named Benoit Mandelbrot published a book. He gave it the title Les Objets Fractals, Fractal Objects. And the word fractal, which he coined from the Latin fractus, meaning broken, described something that had been lurking in mathematics for decades without a name. Mandelbrot had been working at IBM and was given access to their computers, some of the most powerful available at the time. And he used them to visualize mathematical objects that previous generations of mathematicians had described as pathological, too strange to be useful, barely worth studying. Things like the Koch snowflake, the Cantor set, the Sierpinski triangle. The Koch snowflake is built like this. Start with an equilateral triangle. On the middle third of each side, replace that segment with two segments that form a smaller equilateral triangle bump pointing outward. Repeat this on every line segment in the new shape, and repeat it again and again, forever. What you get is a shape with an infinitely long perimeter that encloses a finite area. It's a closed curve that is continuous everywhere, but so jagged that it has no tangent anywhere. It's not differentiable at any point. The Cantor set is weirder. Start with the segment from 0 to 1. Remove the middle third. You're left with two segments. Remove the middle third of each of those. Left with 4 segments. Keep going forever. What's left is uncountably infinite, in some sense more points than the whole numbers, but has total length 0. It's dust, essentially. These objects had been known since the late 19th century. They were discovered by mathematicians like Georg Cantor, David Hilbert, and Karl Weierstrass, while exploring the limits and edge cases of the new rigorous analysis, but they were considered freaks, not relevant to the real world. Mandelbrot said, actually these freaks describe the real world better than smooth Euclidean shapes do. Look at a coastline, measure it with a 1 kilometer ruler and you get one answer. Measure it with a 1 meter ruler and you get a much bigger answer. You're capturing smaller bays and inlets the kilometer ruler missed. Measure it with a 10 centimeter ruler and you get a bigger number still. The measured length keeps growing as you use a finer ruler. Because a coastline is fractal, it has detail at all scales. There's no smooth limit where it becomes a simple curve. The same is true of mountains, clouds, river networks, blood vessel systems, the branching of trees and lungs, the pattern of snowflakes, the structure of cauliflower seriously. A Romanesco broccoli is almost a perfect fractal, even the stock market price over time. The Mandelbrot set, his most famous creation, is built from a simple rule. Take a complex number, c. Start with 0, square the result and add c. Square the new result and add c again. Keep doing this. For some values of c, this process produces numbers that eventually go off to infinity. For others, the sequence stays bounded forever. The boundary between those two sets, the actual Mandelbrot set, is infinitely complicated. No matter how much you zoom in, you find more structure. Spirals within spirals, tiny copies of the whole set embedded in the edges, seahorse shapes and lightning bolt tendrils, all generated from one rule: square and add c. The Mandelbrot set has a Hausdorff dimension of 2. Even though it's technically a curve one-dimensional, it's so infinitely wiggly that it fills space as efficiently as a plane. This is the notion of fractal dimension, a way of measuring how rough or space-filling an object is, which doesn't have to be a whole number. Fractal geometry has found real applications in computer graphics. Fractal terrain generation makes realistic-looking mountains and landscapes. Antenna design. Fractal antennas can be very compact while covering many frequencies. Medicine. The fractal structure of blood vessels and lung tissue is now studied in connection with disease and telecommunications. Mandelbrot's famous summary: clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. Classical geometry describes idealized shapes. Fractal geometry describes the actual shapes in nature. Back when Descartes connected geometry and algebra, he did something simple. He showed that curves in the plane correspond to equations in 2 variables. Algebraic geometry takes this to an extreme. An algebraic variety is the set of solutions to a system of polynomial equations. The parabola y equals x squared is 1. The circle x squared plus y squared minus 1 equals 0 is another. These are curves, one-dimensional objects, loosely speaking, in the plane. But you can write polynomial equations in 3, 4, 10, any number of variables, and the solutions are higher dimensional geometric objects. Things that you can't visualize in the usual sense, but which have genuine geometric structure. They have dimension, they have curvature, they have intersections with other varieties, they have singularities. Algebraic geometry is one of the deepest and most abstract areas of modern mathematics. It connects to number theory in profound ways. Fermat's last theorem, which says there are no positive integer solutions to x to the n plus y to the n equals z to the n for n greater than 2, was proved in 1995 by Andrew Wiles using algebraic geometry in a major way. The proof used elliptic curves, a particular class of algebraic variety, and deep theorems about how they behave. The Hodge conjecture, one of the 7 Millennium Prize problems with a $1 million prize, is a statement in algebraic geometry about which topological objects in a complex algebraic variety can be realized as algebraic cycles. It's been open since 1950. It sits at the intersection of algebraic geometry, topology, and analysis. Convex geometry is the study of convex shapes. Shapes where any line segment connecting 2 points inside the shape stays entirely inside the shape. Balls and cubes are convex. Donuts and stars are not. Convex geometry sounds narrow, but it's connected to optimization, figuring out the best solution to a problem. And convex optimization is one of the most practically important areas of applied mathematics. Machine learning, economics, engineering design, scheduling, all of them rely on convex optimization. The simplex algorithm developed by George Dantzig in 1947, is a method for optimizing over a convex polytope, a flat-sided convex shape. It's still one of the most widely used algorithms in the world. Discrete geometry is about geometric objects that live on grids or discrete structures, not continuous spaces. Counting how many points you can put in a circle with no 3 on the same line. Packing spheres in a box as efficiently as possible, the sphere packing problem. Finding the shortest path through a network. This area has connections to combinatorics, graph theory, and computer science. The Kepler conjecture, which said that the densest way to pack identical spheres in three-dimensional space is the face-centered cubic or hexagonal close packing arrangement, the way you stack cannonballs or oranges at a market, was proposed by Johannes Kepler in 1611. It was proved by Thomas Hales in 1998 using a massive computer-assisted proof that verified thousands of cases. The proof was so complex that it took 12 years of verification before the mathematical community was satisfied it was correct. Computational geometry is the branch dealing with how computers can solve geometric problems. How do you find the convex hull of a set of points efficiently? How do you detect when two polygons overlap? How do you navigate a robot through a cluttered space? These are the questions. The algorithms that answer them power everything from video games to self-driving cars to GIS, Geographic Information Systems mapping. Mesh generation, breaking a complex three-dimensional shape into a mesh of smaller triangles and tetrahedra for finite element simulation, is pure computational geometry, and it's used in engineering to simulate the stress on aircraft wings, the aerodynamics of cars, the blood flow through heart valves. General relativity is the best theory of gravity we have, and it's essentially a geometric theory. So, what does the geometry of spacetime look like? Spacetime is four-dimensional, 3 dimensions of space plus 1 of time. In special relativity, the simpler version, spacetime is flat. It's Minkowski space, which is like Euclidean space, but with a different notion of distance that includes time. The spacetime interval between two events is the square root of the difference in the spatial distance squared minus the time difference squared times the speed of light squared. This different metric, the rule for measuring distances, gives you time dilation and length contraction. In general relativity, this flat Minkowski spacetime is replaced by a curved Riemannian manifold, Lorentzian manifold to be precise, where the curvature varies depending on the distribution of mass and energy. Near a massive star, spacetime curves more. Near a black hole, it curves enormously. A black hole is a region where the curvature of spacetime is so extreme that the escape velocity exceeds the speed of light. The event horizon, the boundary of the black hole, is a surface in spacetime from which no signal can escape. If you cross it, you're falling into a region where all paths lead toward the singularity. The geometry forces you forward just as surely as the geometry of a slope forces a ball downhill. There's no fighting it from inside the event horizon. Stephen Hawking and Roger Penrose proved a series of theorems in the 1960s, the singularity theorems, showing that under certain geometric conditions, singularities are inevitable in solutions to Einstein's equations. These are theorems of differential geometry applied to spacetime, and they have profound physical consequences. Penrose also discovered what are called Penrose tilings, ways to tile an infinite flat plane with only two shapes in a pattern that never repeats but is still ordered. The pattern has five-fold rotational symmetry that can't be achieved by a repeating periodic tiling. These were discovered in the 1970s as a mathematical curiosity, and then in 1984, quasi-crystals were discovered. Real physical materials whose atoms are arranged in Penrose-like non-repeating patterns. Again, mathematics discovered something before physics needed it. A question that's still open: what is the shape of the universe? We know from observations that on large scales, the universe appears to be flat, or very close to flat, meaning the angles of triangles add up to very close to 180 degrees. But that still leaves a lot of possibilities. A flat universe doesn't have to be infinite. Think about a sheet of paper. If you roll it into a cylinder, it's still flat, you haven't curved it. You've just changed its global topology, but it's finite in one direction. If you roll that into a torus donut shape, it's flat and finite in both directions. The universe could be flat and infinite, flat and shaped like a torus, or many other possibilities. The global topology of the universe is a genuinely open question in cosmology. Or the universe could be slightly positively curved, in which case it would be like a three-dimensional sphere, closed, finite, no boundary, and you'd eventually come back to where you started if you traveled far enough in a straight line. Some cosmological models suggest this. Or it could be slightly negatively curved, hyperbolic, in which case it would be infinite, but with the weird angular properties of hyperbolic geometry. There's a field called cosmic topology that tries to look for signatures of the universe's topological structure in the cosmic microwave background, the leftover light from the Big Bang. If the universe is finite and small enough, we might see repetitions in that background radiation, the same pattern in multiple directions, because light from a single source has wrapped around. So far, no such repetitions have been found, which means either the universe is infinite or it's finite but bigger than the observable universe. We're living in a period where the relationship between geometry and computation is deeper than it's ever been. Machine learning uses geometry constantly. The high-dimensional spaces in which neural networks operate, where each dimension represents a different feature, have geometric structure. Points in these spaces correspond to data points, and the goal of learning is often to find a geometric boundary that separates different categories. Geometric deep learning is a framework that applies the tools of differential geometry to machine learning on non-Euclidean data, graphs, point clouds, meshes. In 2024, Google DeepMind's Alpha Geometry system solved geometry problems at a level approaching an International Mathematical Olympiad gold medalist. This is significant because geometry problems, especially competition geometry, require a kind of creative intuition that was thought to be beyond AI. You have to see auxiliary constructions, unexpected relationships, non-obvious approaches. Alpha geometry used a combination of a language model to propose geometric constructions and a symbolic solver to verify their work. It solved 28 out of 30 Olympiad geometry problems correctly. Computer graphics relies heavily on geometry at every level. Three-dimensional models are triangle meshes. Rendering them requires calculating how light interacts with surfaces, which is geometry. Physics simulation, how objects collide and deform, is geometry. Animation, how a character's body moves, uses differential geometry of curved surfaces. Texture mapping, projecting a two-dimensional image onto a three-dimensional surface, is a geometric problem of parameterization. Robotics needs geometry for motion planning, how to move a robot arm from one position to another without colliding with obstacles. This is a problem in the configuration space of the robot, a high-dimensional space where each point represents a possible arrangement of the robot's joints, and you need to find a path through this space that avoids the regions corresponding to collisions. Medical imaging uses geometry extensively. MRI and CT scans produce three-dimensional images of the body. Extracting meaningful information from those images, finding tumors, measuring organ volumes, tracking changes over time, requires geometric processing. And surgical planning increasingly uses three-dimensional geometric models of the patient's anatomy to plan complex procedures. Topological data analysis (TDA) is a newer field that uses tools from algebraic topology, particularly something called persistent homology, to analyze the shape of data. If you have a cloud of data points in some high-dimensional space, TDA can tell you about the holes and voids in that cloud at different scales, and those topological features often correspond to meaningful structure in the underlying system. It's been applied to analyzing protein folding, studying the structure of the brain's neural activity, and finding cancer cells in tissue samples. Quick side trip to something beautiful. In 3 dimensions, there are exactly 5 regular convex polyhedra, shapes where all faces are the same regular polygon and all vertices are surrounded by the same arrangement of faces. This was proved by Euclid at the end of the Elements, and it's one of the most beautiful existence theorems in all of mathematics. The 5 solids are the tetrahedron 4 equilateral triangular faces, the cube 6 square faces, the octahedron 8 equilateral triangular faces, the dodecahedron 12 pentagonal faces, and the icosahedron 20 equilateral triangular faces. Why exactly 5? Because you can only make a convex solid if the faces around each vertex add up to less than 360 degrees. If they added up to exactly 360 degrees, you'd get a flat plane. More than 360 and it folds the wrong way. Triangles have angles of 60 degrees. Put 3 around the vertex, 180 degrees, less than 360, that gives you the tetrahedron. 4 triangles, 240 degrees, octahedron. 5 triangles, 300 degrees, icosahedron. 6 triangles, 360, flat, done. Squares have 90-degree angles. 3 squares around a vertex, 270 cube. 4 squares, 360, flat, done. Pentagons have 108 degrees. 3 pentagons, 324 dodecahedron. 4 pentagons, 432. More than 360 doesn't work, done. Hexagons have 120 degrees. 3 hexagons, 360, flat, done. And that's all you can have. 5 solids. The Greeks were deeply impressed by this fact. Plato, in a dialogue called the Timaeus, associated each solid with one of the classical elements, the tetrahedron with fire, its sharp and stabby, the cube with earth, it stacks stably, the octahedron with air, the icosahedron with water, and the dodecahedron, the most complex, with the heavens or the cosmos. Johannes Kepler, in 1609, tried to fit the orbits of the 6 known planets into a nested arrangement of the 5 Platonic solids. It was wrong. Orbits are ellipses, not spheres, and there are now 8 known planets. But it was a beautifully geometric wrong answer, and the attempt drove him to do more precise calculations that led him to his actual laws of planetary motion. In the 20th century, viruses were discovered to have icosahedral geometry. The capsid, the protein shell of a virus, like an adenovirus or a herpes virus, is built from proteins arranged in icosahedral symmetry. This turns out to be structurally optimal. The icosahedron gives the most volume for the least surface area among the Platonic solids, and its symmetry means the protein shell can be built using only a small number of distinct protein types repeated many times. Underlying all of geometry is the concept of symmetry, and symmetry has a precise algebraic description through the theory of groups. A group is a set of elements with a rule for combining them, like multiplication, that satisfies 4 properties. It's associative, there's an identity element, every element has an inverse, and combining 2 elements always gives another element in the group. The symmetries of any geometric object form a group. The symmetries of a square, rotations by 90, 180, and 270 degrees, plus 4 reflections, form a group of order 8 elements. The symmetries of a circle form an infinite group you can rotate by any angle. The symmetries of a sphere form the rotation group SO3. Felix Klein's Erlangen program from 1872 said that you can characterize any geometry by its group of symmetries. Euclidean geometry is characterized by the Euclidean group, all rotations, reflections, and translations. Projective geometry has a larger symmetry group, projective transformations. Hyperbolic geometry has its own symmetry group. Group theory and geometry are deeply intertwined in modern physics. The Standard Model, our current best description of elementary particles, is essentially a statement about symmetry groups. The photon carrier of electromagnetism comes from U1 symmetry. The W and Z bosons, weak force, come from SU2 symmetry. The gluons, strong force, come from SU3 symmetry. The particles and forces of nature are characterized by their symmetries, and those symmetries are geometric. Crystallography, the study of crystal structures, is pure geometry and group theory. The possible ways to arrange atoms in a repeating pattern in 3-dimensional space are classified by the 230 space groups. Every crystal falls into one of these 230 symmetry classes. So where is all of this heading? Let's think about the open questions and the research directions that might be where the next big things are going to come from. The biggest open problem touching geometry and physics is quantum gravity. General relativity describes gravity geometrically as the curvature of spacetime. Quantum mechanics describes everything else, particles, forces, fields, through probability and quantum states. The problem is that these two theories are fundamentally incompatible. When you try to apply quantum mechanics to curved spacetime, you get nonsensical infinities. Loop quantum gravity is one approach that tries to make spacetime itself quantized, discrete, rather than continuous. In this theory, space itself is made of tiny loops or spin foam structures, and what we experience as smooth, continuous spacetime is just the large-scale average of these discrete geometric structures, in the same way that water looks smooth even though it's made of molecules. The minimum length scale would be the Planck length, about 1.6 times 10 to the minus 35 meters, immeasurably smaller than anything we can currently probe. This is a fundamentally geometric theory where the geometry is quantized. String theory, the other main approach to quantum gravity, also relies heavily on geometry in the form of Calabi-Yau manifolds and other exotic mathematical structures. There's been an extraordinary amount of mathematical progress in string theory, even though its physical predictions remain unconfirmed experimentally. Geometric deep learning is going to keep growing. The idea that data has geometry, that the right way to process image data is to respect its spatial symmetry, and the right way to process molecular data is to respect its rotational symmetry, is making machine learning models much more efficient and capable. Equivariant neural networks, which automatically preserve geometric symmetries, are becoming central to science applications. They're being used for protein structure prediction, drug discovery, climate modeling. Topological data analysis is also going to grow. As datasets get bigger and higher dimensional, extracting structural information becomes harder. TDA provides tools that are coordinate-free, don't depend on your choice of coordinate system, and can identify structure at multiple scales simultaneously. There are open questions about how to make TDA computationally faster and how to best apply it to specific domains. The geometrization theorem, proved by Perelman building on Thurston's program, completely classified all three-dimensional manifolds by their geometric structure. It's a monumental theorem. The four-dimensional version remains much less understood. Four-dimensional topology is still wild and strange. There are exotic smooth structures on four-dimensional space that don't exist in any other dimension, and understanding this is an active area. Algebraic geometry keeps producing surprises. Mirror symmetry, a connection between pairs of Calabi-Yau manifolds that was discovered through string theory, has been a source of mathematical conjectures and theorems for 3 decades now, and the pattern of results it predicts keeps being verified. Something deep and not fully understood is going on. There's active research into the geometry of numbers, which is really the geometry of high-dimensional lattices to regular grids in many dimensions. The best way to pack spheres in high dimensions, and how many spheres can touch a given sphere in a given dimension, are open questions above a certain dimension. A major breakthrough came in 2016 when Marina Wiazowska proved that in dimension 8 and in dimension 24, the densest sphere packings are given by the E8 lattice and the Leech lattice, respectively. These are extraordinarily symmetric lattices with connections to string theory and the monster group in algebra. The Langlands program, maybe the biggest research program in all of mathematics, connects number theory, geometry, and representation theory in ways that are still being worked out. It was proposed by Robert Langlands in 1967 in a letter to André Weil, and has been described as a grand unified theory of mathematics. It predicts deep correspondences between things that look completely unrelated, the behavior of solutions to polynomial equations over finite fields, and the representation theory of Lie groups, connected through automorphic forms. Geometric Langlands, the version of this program for function fields and algebraic geometry, saw a breakthrough in 2024 when a massive collaborative paper proved one of the main conjectures. But the full arithmetic Langlands program is still a long way from complete. Quantum geometry is an area where researchers are exploring what it means to do geometry with quantum coordinates, non-commutative spaces where position measurements in different directions don't commute, like quantum operators. This connects to non-commutative geometry developed by Alain Connes, and there are speculations that the geometry of spacetime at the Planck scale might be non-commutative. AI is going to change geometry research itself, not just apply it. Alpha geometry is a first step. As AI systems get better at formal reasoning, they'll be able to explore mathematical spaces that are too large for humans to search manually, trying millions of approaches to a conjecture, verifying proposed proofs, finding unexpected connections between different areas. The Lean theorem prover and other formal proof systems are making it possible to verify complex proofs with certainty. MathLib, a library of formally verified mathematics, already contains thousands of theorems in geometry and related areas. Within the next 20 or so years, it's quite plausible that AI will prove new geometry theorems that humans haven't been able to. It's already come close in geometry competition problems. The step to actual research level results is a big one, but the trajectory points there. There's a whole branch of geometry we haven't talked about yet that runs through everything from navigation to music to quantum mechanics, trigonometry. And it's worth spending time on because it's one of those things that sounds scary and technical until you see what it actually is, and then it clicks and you realize it's been describing the world all along. Start with a right triangle. You have a right angle on one corner, an angle called theta on another corner, and the third angle is whatever's left to make the angles add up to 180 degrees. The three sides have names relative to the angle theta. The hypotenuse, the long side, opposite the right angle, the opposite side, the side directly across from theta, and the adjacent side, the side next to theta that isn't the hypotenuse. Three ratios of these sides are the most important. The sine of theta is opposite over hypotenuse. The cosine of theta is adjacent over hypotenuse. The tangent of theta is opposite over adjacent. These three ratios, sine, cosine, tangent, are the heart of trigonometry. That matters a lot. If you know an angle and one side length of a right triangle, you can find all the other sides. If you know the angle theta and the hypotenuse length, then the opposite side is hypotenuse times sine of theta, and the adjacent side is hypotenuse times cosine of theta. You've converted an angle measurement into a distance. That's incredibly powerful for navigation, surveying, and astronomy. Ancient astronomers used something similar. They worked with chords instead of signs, but the idea was the same. Hipparchus of Nicaea around 120 BCE, compiled what may have been the first trigonometric table. Ptolemy extended this into the detailed tables in the Almagest. Indian mathematicians, particularly Aryabhata, in around 500 CE, worked with half chords, which are essentially sines, and their work was more efficient than the Greek chord approach. Now, extend the idea beyond right triangles. The sine and cosine functions are defined for any angle, not just angles between 0 and 90 degrees. As the angle increases from 0 to 90 degrees, sine goes from 0 to 1. From 90 to 180, sine goes from 1 back to 0. From 180 to 270, sine goes negative, reaching -1 at 270. Then it comes back to 0 at 360, a full circle. This means sine and cosine are periodic functions. They repeat their values every 360 degrees or 2 pi radians, and periodic functions describe waves, the motion of a pendulum, the vibration of a string, the pressure oscillations of sound, the oscillating electric and magnetic fields of light, the probability amplitude of a quantum particle. All of these are described at their core by sine and cosine. The Fourier transform, developed by Joseph Fourier in the early 19th century, says that any periodic function can be broken into a sum of sines and cosines of different frequencies and amplitudes. Your voice is a complex waveform. Your phone compresses it into a digital signal using Fourier analysis, breaking it into frequency components, discarding the ones you can't hear, and transmitting just enough information to reconstruct the sound at the other end. Every compressed audio file, every digital photograph JPEG compression uses a two-dimensional Fourier transform. Every signal processing application rests on this geometric relationship between angles and waves. The unit circle is the most elegant way to see all of this. Draw a circle with radius 1 centered at the origin. As you move counterclockwise around the circle, the x-coordinate of your position traces out the cosine function, and the y-coordinate traces out the sine function. The angle measured counterclockwise from the positive x-axis gives you the input. The x and y coordinates give you cosine and sine, all at once in one picture. And then there's Euler's formula. Published by Leonhard Euler around 1748, it states e to the power of I times theta equals cosine of theta plus I times sine of theta, where e is the base of natural logarithms, roughly 2.718, I is the square root of -1, and theta is any angle. This connects the most important constants in mathematics, e and pi. When you set theta equal to pi, you get the famous Euler's identity, e to the I times pi plus 1 equals 0. And it reveals that sines and cosines are really just different aspects of a complex exponential function. The geometry of circles and the analysis of exponential functions are the same thing, seen from different angles. This is maybe the most beautiful single equation in all of mathematics, and it's a geometric statement. Let's bring this all the way down to earth for a minute. Forget the abstract theory. Watch coordinate geometry do something real. Say you're making a video game. You've got a character that can move around a two-dimensional world. The character's position is a pair of numbers, x, y. Their velocity is another pair, vx, vy. Every frame of the game, you update the position. New x equals old x plus vx times time elapsed. New y equals old y plus vy times time elapsed. That's it, the character moves. But then you want the character to jump, so you add a vertical acceleration. Vi decreases each frame by the gravitational constant times time elapsed. The character accelerates downward. Plot the path of the character over time. It's a parabola, the same conic section that Apollonius was studying 2,000 years ago, the same curve you get when you slice a cone at just the right angle. The physics of a jumping game character traces ancient Greek geometry. Now you want to check if the character hits a wall. The wall is a line segment. The character is a circle for collision purposes. You need to know if the circle and line segment overlap. This is a distance calculation. Find the closest point on the line segment to the center of the circle and check if that distance is less than the radius. Pythagorean theorem. Again, want the character to face the direction they're moving? Calculate the angle of the velocity vector. If Vx equals 1 and Vy equals 1, the angle is 45 degrees. In general, the angle is the arctangent of Vy divided by Vx. Trigonometry. Want a camera that follows the character but stays within the level boundaries? Smooth interpolation between two positions over time. Linear interpolation. Position equals start plus t times end minus start, where t goes from 0 to 1. If you want it to ease in and ease out smoothly, you use a cubic function, another application of polynomial algebra and geometry. Your entire experience of any three-dimensional video game or movie is a series of geometric transformations applied 60 or more times per second. Every vertex of every triangle in the three-dimensional model is multiplied by rotation matrices, projection matrices, and view matrices. Lighting is calculated using dot products of vectors. Shadows are tested by casting rays and checking for intersections. Normal maps, bump maps, ambient occlusion, all geometric calculations. The photorealistic images in modern video games and movies are real-time geometry. There's a corner of geometric history that's a little more mystical, or seems that way, but has real mathematical substance underneath it. The golden ratio. Define it geometrically. Take a line segment and divide it into two parts. The golden ratio is the division point, where the ratio of the whole segment to the longer part equals the ratio of the longer part to the shorter part. If the whole is 1 and the longer part is phi, then 1 over phi equals phi over 1 minus phi. Solving this gives phi equals 1 plus square root of 5 divided by 2, about 1.618. This number shows up in geometry in places that seem almost spooky. The diagonal of a regular pentagon has length phi times the side length. The golden rectangle, where the ratio of length to width is phi, has the property that if you cut a square from one end, the remaining piece is another golden rectangle. You can keep cutting squares from golden rectangles forever, and you always get another golden rectangle. The spiral through the corners of these nested squares converges to a specific point, the Nautilus shell spiral. The Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21, 34, where each number is the sum of the previous two, has the property that the ratio of consecutive terms approaches the golden ratio. Fibonacci numbers appear in the spiral arrangements of seeds in a sunflower, the scales on a pine cone, the arrangement of leaves on a stem called phyllotaxis. These are real patterns in real plants. The geometric reason is that golden angle arrangements around 137.5 degrees, which is 360 divided by phi squared, are optimally efficient for packing seeds without any row aligning directly with another row. People have claimed the golden ratio appears in the Parthenon, in the proportions of the human body, in the pyramids. Many of these claims are exaggerated or simply wrong. You can find phi in almost anything if you measure enough things and pick the ratios you like. But the places where it genuinely appears, the regular pentagon, the Fibonacci sequence, phyllotaxis, are real and geometrically meaningful. When Descartes put coordinates on the plane, the natural question was, what about 3 dimensions? You add a third coordinate, call it z, and now every point in 3-dimensional space is a triple x, y, z. Surfaces in 3-dimensional space correspond to equations in 3 variables. The sphere of radius 5 centered at the origin is x squared plus y squared plus z squared equals 25. The plane that contains all points with z equal to 0 is just z equals 0. Infinite flat surface described by a single simple equation. What about 4 dimensions? You add a fourth coordinate, call it w or t. Now a point is a quadruple x, y, z, w. 4-dimensional objects are described by equations in 4 variables. You can't visualize them directly, but you can work with them algebraically, and everything you know about lower dimensional geometry extends in a principled way. A 4-dimensional sphere, sometimes called a globe, consists of all points where x squared plus y squared plus z squared plus w squared equals r squared. Its 3-dimensional surface, the boundary, is actually a 3-dimensional sphere. If you take cross-sections of a 4-dimensional sphere at different heights, different values of w, you get ordinary 3-dimensional spheres that start small, grow to a maximum radius, then shrink back to a point, just as cross-sections of an ordinary sphere at different heights are ordinary circles that grow and shrink. This pattern extends to any dimension. An n-dimensional sphere has an n-1-dimensional surface, and the formulas for volume and surface area have nice patterns in terms of pi and the dimension. The dimensionality of space matters enormously for physics and mathematics. In 1 dimension, you can only walk forward and backward. In 2 dimensions, you can encircle things. In 3 dimensions, you can have knots, curves that loop around themselves in a way that can't be undone without cutting. In 4 dimensions, there are no knots. You can always slip a loop free in the extra dimension. In exactly 4 dimensions, there's a weird phenomenon. There are infinitely many distinct, smooth structures on 4-dimensional space, which doesn't happen in any other dimension. This is Donaldson's theorem, proved in 1983, using gauge theory, which comes from physics. 4 dimensions is special in ways that are still not completely understood. Probability and geometry meet in some unexpected places. Buffon's needle problem, posed by Georges-Louis Leclerc, Comte de Buffon, in 1777. Suppose you have a floor with parallel lines ruled across it, spaced some distance d apart. You drop a needle of length L where L is less than or equal to d. What's the probability that the needle crosses one of the lines? The answer is 2 times L divided by pi times d. There's pi in there. The probability of a needle crossing a line depends on pi, the circle constant, even though there are no circles in the problem. The reason is that the needle's orientation is uniformly random over all angles, and integrating over all angles brings pi into the calculation. You can actually use this to estimate pi experimentally. Drop thousands of needles and measure the fraction that cross the lines. That fraction converges to 2L divided by pi d, so you can solve for pi. People have done this. It's inefficient as a way to estimate pi, but it's beautiful. Geometric probability shows up in picking a random chord of a circle. What's the probability that a random chord is longer than the side of an inscribed equilateral triangle? The answer depends on what you mean by random chord. Different natural ways of defining randomness give different answers: 1/3, 1/2, or 1/4, depending on how you pick the random chord. This is Bertrand's paradox, and it shows that random is not a simple concept. You have to specify precisely what probability distribution you're using. Random geometric processes, random tilings, random planar maps, random surfaces are studied in probability theory and connect to statistical physics, quantum gravity, and conformal field theory. The Gaussian free field is a random surface that shows up as the scaling limit of many discrete models. The Schramm-Lohner evolution describes random planar curves with beautiful conformal symmetry properties. These are genuine research frontiers where probability, geometry, and physics meet. When you have a set of data points, those points live in a space. If each data point has 500 features, 500 numbers describing it, then each data point is a point in 500-dimensional space, and that space has geometry. One of the most striking facts about high-dimensional spaces is that they behave very differently from the low-dimensional ones our intuition is built for. In high dimensions, almost all of the volume of a sphere is near the surface. The interior is essentially empty. Almost all pairs of vectors are nearly orthogonal. If you pick a random point inside a high-dimensional sphere, it's almost certainly very close to the surface. These facts are collectively called the curse of dimensionality, and they explain why many intuitive geometric algorithms fail in high dimensions. But data isn't usually uniformly spread through all 500 dimensions. Natural data tends to lie near a lower dimensional submanifold, a curved surface of much lower dimension embedded in the high dimensional space. Images, for example, don't explore all possible combinations of pixel values. Almost all possible pixel combinations would look like random static. The actual images we care about, faces, landscapes, text, form a much lower dimensional manifold embedded in pixel space. Manifold learning is the practice of finding that lower dimensional manifold. Algorithms like t-SNE, t-distributed, stochastic neighbor embedding, or UMAP, uniform, manifold approximation, and projection, try to find a 2 or 3-dimensional representation of your data that preserves its geometry as well as possible. You can then visualize it and often discover structure, clusters, trajectories, hierarchies that wasn't obvious in the original high-dimensional representation. Convolutional neural networks, which power image recognition, are built on the geometry of images. They use translation symmetry, the fact that a cat in the top left corner of an image is the same kind of object as a cat in the bottom right corner. The convolution operation exploits this symmetry to drastically reduce the number of parameters needed. Pooling operations use the geometry of scale. Nearby pixels are likely to be similar. Graph neural networks handle data that has network structure, molecules, social networks, road networks, by passing information between connected nodes in a way that respects the graph's topology. The graph is a geometric object, a combinatorial one, without exact positions, but with connectivity structure, and the neural network respects that geometry. Diffusion models, the kind behind image generation systems like DAL-E or Stable Diffusion, can be understood geometrically. The model learns to reverse a process that gradually adds random noise to images. The learned reverse process follows a flow on the manifold of natural images, and the mathematical framework for these flows is closely related to stochastic differential geometry. Soap films are really good at geometry. If you dip a wireframe into soapy water and pull it out, the soap film that forms across the frame is the surface of minimum area spanning that wire boundary. This is called a minimal surface, and the soap film finds it automatically. Surface tension pulls the film tight until every part of the surface is as small as possible. Minimal surfaces have been studied since Euler and Lagrange in the 18th century, but the modern mathematical treatment uses geometric measure theory, a 20th century framework developed by Herbert Federer and Wendell Fleming. The key insight is that even for very irregular or complicated boundaries, you can still find the minimum area surface, but you need a more general notion of surface that allows for singularities and branching. The plateau problem, given a closed curve, find the surface of minimal area spanning it, was solved in its modern form in 1930 by Jesse Douglas, who received the first Fields Medal for this and Tibor Rado. But the full generality, allowing for higher dimensions and arbitrary topological complexity, required geometric measure theory. Minimal surfaces aren't just soap films. They appear in architecture, thin shell structures that minimize material while maintaining strength. They appear in materials science. Some block copolymers form minimal surface interfaces. They appear in biology, the shape of cell membranes. And in differential geometry, they're connected to deep theorems about the topology of three-dimensional manifolds. The positive mass theorem, a result about the geometry of spacetimes in general relativity, was proved by Richard Schoen and Xing-Tung Yao in 1979 using geometric measure theory and techniques from minimal surface theory. The theorem says that if an asymptotically flat spacetime satisfies the Einstein equations and the energy conditions are met, then the total mass of the spacetime is non-negative. A physically necessary result that had eluded proof for decades. There's something else worth saying about why any of this matters beyond the specific results. Geometry teaches a way of thinking. You start with a small set of things you're sure about. You reason step by step. Each step is justified by what came before. And at the end, you have a conclusion that's as certain as those initial assumptions. This is the deductive method, and it comes from geometry. Every science that uses mathematical models is doing something Euclid started. You write down equations that you believe describe the system. You derive consequences from those equations. You check the consequences against observation. The whole of mathematical physics is structured this way, and there's something humbling about the history we've walked through. The Egyptians needed to survey flooded fields. The Greeks wanted to understand why things work, not just that they do. Euclid built a logical system that stood basically unchallenged for 2,000 years. Then it turned out there were consistent alternatives, that you could change one rule and get a completely different but equally valid geometry. And then Einstein showed that one of those alternatives, Riemannian geometry, actually describes the universe we live in. Nobody who built the Great Pyramid of Giza was thinking about the curvature of space-time. Nobody who figured out the 3-4-5 triangle for making right angles was thinking about abstract groups of symmetries. Nobody who first noticed that a coastline gets longer the more carefully you measure it was thinking about fractal dimensions. But all of those threads connect. The rope stretched across a muddy Egyptian field, the axioms in Euclid's Elements, the curved saddle of hyperbolic space, the endlessly zooming edge of the Mandelbrot set, the curvature tensor in Einstein's field equations. They're all part of the same story. All ways of answering the same question the human brain has been asking since before we had language for it. There's also something worth noting about how the history of geometry mirrors the history of human ambition. Early geometry was purely practical. You measured what you needed because survival depended on it. Then the Greeks turned measurement into understanding. They wanted to know not just what the answer was, but why it had to be that answer. Then the Islamic scholars preserved and extended that understanding through a period when Europe had lost it. Then the Renaissance figured out how to connect geometric intuition to algebraic calculation. Then calculus opened up the study of the infinitely small and the continuously changing. Then non-Euclidean geometry cracked open the question of whether Euclid's system was the only possible one or just one of many. Then Riemann gave a general framework for curved spaces of any dimension. Then Einstein used that framework to describe gravity. Then topology revealed the global shape of spaces and the holes within them. Then fractals showed that nature was rougher and weirder than any classical geometry suggested. And now we're working on quantizing geometry itself, trying to understand what space and time are made of at the smallest scales. Every generation of mathematicians thought they were getting close to the end. Euclid's Elements was so complete it seemed like it might be the final word on geometry for a long time. Then non-Euclidean geometry arrived. When Riemann presented his framework, it might have seemed like the final general setting. Then Hilbert formalized everything more carefully and revealed hidden gaps even in Euclid's work. When topology classified all surfaces in 2 dimensions and then all 3-dimensional spaces, it might have seemed like geometry was being wrapped up. Then 4-dimensional geometry turned out to be wild and strange in ways that still aren't understood. The subject keeps growing, not just getting more detailed within an established framework, but actually expanding into fundamentally new territory. New kinds of geometry are still being invented or discovered depending on your philosophical view. And every new kind of geometry seems to eventually find a use in physics or computer science or biology that nobody anticipated. That pattern, math developed for abstract reasons, turning out to be exactly what physics needs decades or centuries later, is one of the most mysterious and beautiful things about mathematics. Riemann's geometry waited 60 years for Einstein. Conic sections waited 2,000 years for Kepler. Non-commutative algebra waited a century for quantum mechanics. Something about working out the pure logic of geometric systems seems to be working out the logic of physical reality itself. Maybe that shouldn't be surprising. We evolved in a physical world. Our brains developed to navigate it. The patterns we find compelling, the symmetries we notice, the regularities we seek out, the problems we find tractable, these emerged from living in this universe. When mathematicians trust their geometric intuitions and follow them, they're trusting something that was shaped by reality, and so they keep finding reality. Or maybe it's selection bias. We notice the times mathematics anticipated physics and forget the many times it didn't. The jury is genuinely still out, but the history is undeniable. Every time someone thought geometry was done, it turned out to be just getting started. What is the shape of everything? We don't have the final answer. We're closer than we've ever been. And the tools we've built along the way, the proofs, the theorems, the equations, the algorithms, are some of the most beautiful things human beings have ever made. Thanks for watching. And if you made it this far, through the Nile floods, and the Greek proofs, and the curved space-time, and the fractal coastlines, and the quantum geometry, you've done something most people never do. You followed one thread from the very beginning of recorded human thought to the absolute edge of what we currently know. That's a real thing. Geometry is that long and that deep, and it's nowhere near finished.